In this video, we're going to talk about power series and Taylor polynomials. So power series is a kind of series which involves a variable. So generally, a power series is a series of the following form. So the sum k equals 0 to infinity of ck times x to the k. So these are the terms. And if you write out the individual terms, they look like this. So where x is a variable, and the power of x increases by 1 each term, and the ck's are the coefficients, so C0, C1, C2, which will typically be constants that depend on k. And sometimes it's going to be convenient to center a power series at some number a, and then we'll write the series in this form, so we replace x with x minus a in each of the terms. So part of the usefulness of using power series, we'll see, is that the partial sums of power series are just ordinary polynomials of degree n. So if you write out the partial sums, it just looks like this. So one case which we'll use power series for is the following situation. So we're going to be interested in looking for the values of x for which a given power series will converge. And so when the power series converges, it's going to converge to a function f of x. And then so we can use the partial sums of the power series to approximate the function f of x with polynomials. So the idea is that you can have a complicated function f of x, so especially for transcendental functions like the exponential function or the trig functions sine and cosine. So those things are typically difficult to calculate, and so then we can approximate them with polynomials, which are very simple to calculate with because they only involve algebraic operations of addition and multiplication and so on. So the way we'll do this approximation is by using what's called Taylor polynomials. Okay, so let me first write down what a Taylor polynomial is. So suppose we have a function f of x that we're interested in, and that it has derivatives at least to the nth order. Then the associated nth Taylor polynomial of f of x is given by the following formula. So the nth Taylor polynomial Pn of x is the sum k equals 0 to n of ck times x minus a to the k. So it's just the nth partial sum of a power series, and the coefficients have the following formula. So the ck is equal to the kth derivative of f evaluated at a divided by k factorial. So let me make a note on the notation here, the kth derivative of f. And so f of 1, f upper 1 is the same as f prime. The second derivative of f is the same as f double prime. The third derivative of f is f triple prime. And then this notation just means to take that derivative and evaluate it at a. So again, the numerator here is to evaluate the appropriate derivative at the number a. So writing down each individual term of the Taylor polynomial, it'll look like the following. So Pn of x, so the first term is when k equals 0, right? So the c sub 0 and then the exponent here is 0, so then there's no x term. And then the next term is when k equals 1, so the coefficient is c1. Actually, let me write out the coefficient. So c0 plus c1 times x minus a plus c2 times x minus a squared, and so on. So c0 is using this formula, right? So the 0th derivative of f is just the original function, and 0 factorial is equal to 1. So this is just f of a. And then here c1, so k equals 1, so that will be the first derivative of f, evaluated at a, divided by 1 factorial, which is again equal to 1, times x minus a. And c2 would be the second derivative of f, evaluated at a, divided by 2 factorial, times x minus a squared, and so on, until you get to the nth term, which will be the f to the nth power, evaluated at a, divided by n factorial, or x minus a to the nth power. So this is generally what a Taylor polynomial will look like. And so referring back to what I said earlier, the idea is to approximate complicated functions with polynomials. So we'll see that f of x is approximately equal to Pn of x for values of x close to a. And the higher the degree you take, the better the approximation. So as an example of where we get the approximations, we've actually seen some already. Right, so I'll write out P1 of x. So write this out for P1. You see that it's equal to f of a plus f prime of a times x minus a. Right, so it's up to the first degree, and this is the same as the linear approximation that you learned in Calc 1. And if I take P2 of x, so it's the Taylor polynomial up to the second degree term, this is called the quadratic approximation, because you're approximating a function with a quadratic polynomial. Okay, so let's see how we can use Taylor polynomials to approximate a function. So we're going to try to approximate the natural log function. So let's approximate the natural log of 1.02 using a linear approximation and a quadratic approximation. Okay, so because the function is the natural log, so we take f of x to be the natural log of x, and we want to choose the center a to be a simple number that's close to what we're trying to approximate. So since 1.02 is close to 1, we use a equals 1. So we're going to center the Taylor polynomial at 1. Okay, so first the linear approximation. So again, the formula for the linear approximation, P1 of x, is f of a plus f prime of a times x minus a. So again, we have a is equal to 1. F of x is equal to the natural log of x. And so f of 1 is the natural log of 1, which is equal to 0. And we also need the derivative. So f prime of x, the derivative of natural log is 1 over x. And so f prime of 1 is 1 over 1, which is equal to 1. So now that we have this computed, we can just plug it into the formula to get the linear approximation. So P1 of x, f of 1 is equal to 0, f prime of 1 is equal to 1, and times x minus a, which is equal to 1. So P1 of x, so it's simplified, this is just x minus 1. And so now we use the Taylor polynomial to approximate the function. The natural log of 1.02 is approximately the Taylor polynomial evaluated at this point, which is equal to 1.02 minus 1, which is 0.02. So we're saying that the natural log of 1.02 is going to be close to 0.02. So now let's take a look at the quadratic approximation. So the formula for P2 of x is f of a plus f prime of a times x minus a. So we have to go up to the secondary term, which involves the second derivative. And then 2 factorial is equal to 2. So again, we have to do the same thing as before. Compute the function values and the derivatives. So f of x is equal to the natural log of x. So f prime of x is equal to 1 over x. And f double prime of x, so the derivative of this is minus 1 over x squared. F of 1 is again equal to 0. F prime of 1 is equal to 1. And f double prime of 1 is minus 1 over 1, which is equal to minus 1. And so I'm plugging everything into the Taylor polynomial. F of P2 of x, 0 plus 1 times x minus 1 plus minus 1 over 2 x minus 1 squared. And so simplifying this, we get that P2 of x is equal to x minus 1 plus minus 1/2 x minus 1 squared. So now again we use the polynomial to approximate. So the natural log of 1.02 is approximately equal to P2 evaluated at 1.02. So plugging in 1.02, you get 1.02 minus 1 minus 1/2 1.02 minus 1 squared. And then calculating this, we get 0.0196. So using a calculator, we see that these two are actually fairly close approximations. The natural log of 1.02 is equal to 0, is approximately 0. Up to 4 decimal places. This is 0.0198. And so the area of the linear approximation is just slightly off. So the error of a linear so it will be 0.02 minus 0.0198, which is just off by 0.0002. So just 2/10,000ths off. And the quadratic approximation likewise is 0.0196 minus 0.0198. This is also just 2/10,000ths off of the actual value. So we see that both are good approximations, and you can get better and better approximations by taking a higher order Taylor polynomial.